Okay, so I think we should start. Can you guys actually keep adding people as they are coming? So I guess you will also be able to admit people into the meeting. Like if they come in between and you see any admit requests, so you can put them in. Fine. So, okay, these sessions are meant to be for problem solving, and we are going to be looking at some sample problems. Apart from the problems, you can also discuss any of the queries that you might have, any doubts, any clarifications that you need, but only for the course content, like not for the technical things, like because we have limited time of an hour. So we are going to mostly take up like subject related questions and not technical issues like maybe quiz submission problems or any other technical difficulties you can put on the forum itself. So here we are going to strictly look at questions related to the content of the course. So I guess we have enough people, so we should just have an introduction first. So these sessions are meant to be very interactive in nature. So it will only help you guys if you are going to ask questions and also answer them. So we are going to go through problems together in these sessions, and one by one I'll be showing you the problems, and what you'll have to do is try to solve them yourself and answer them in the chat. And if in case you do not get it, then we are going to discuss the solutions and you can ask any of your queries that you might have. Okay. So as an introductory remark, also, so you guys should be really active in the chat, like just keep talking, and like you can just send in your messages on the chat, and also you can just switch on your mic or your video, whatever you're comfortable with, and don't hesitate to ask or comment about anything. Whatever you feel like is necessary, just don't hesitate, stop me. Don't think that what others would think, or you're just one person who might have this question. That is not true. Like your question might be common between a lot of folks. So it's better if you just keep asking questions and just keep like as many interruptions as we have in the throughout this session. Like that will be a successful session. So let's just start with some question. I need some answers from you guys. As in, how are you liking the course so far? And if you have attempted quiz 1, don't hesitate to like just open your mic. We should just get comfortable with that notion. Tell me, like, are you finding the course too difficult or too easy, or are you just completely lost in it, whatever is it? Like, I just want some feedback from you guys. Anyone? I hope I'm audible. Are you guys able to hear me? Okay.
Yeah.
Okay. Thanks, Mihir. Alright, so how many of you guys have attempted the first quiz? Maybe they have already attempted it. The due date is, I think, 10th of August. And okay, Mitch, do you find it? Did you find it easy, or did you find it like there were some tricky questions in it that you didn't, or maybe some concepts that like you did not, like it didn't hit you or something? Okay, so we have moderate, and I guess people find it moderate generally. Yeah, I think so. What we are going to do in this session is the course content of the first week. So many of the questions that we are going to cover are the similar questions that you will find in your first quiz, and so that will actually help you if you haven't attempted it so far. So you can go back and attempt it again, and you will find it more familiar. Like you will cover most of the content like in these sessions, and that is the whole idea, that these sessions should help you in solving your quizzes and your assignments. So we get the content. Yeah, someone was saying something. Okay, so Gurkhan says the big O notation needs more explanation, so we are going to be looking at big O notation, a lot of examples and the core concept of big O today. And last question was a bit challenging. Okay, that is good. Like there should be something challenging, it shouldn't be really easy, otherwise it loses the purpose. So week 1 assignment is going to get uploaded soon, programming assignment. Now the quiz 1 and quiz 2 have been uploaded, and you also get a programming assignment too. So this session is recorded, and the link will be there on the YouTube, and I think they'll also post it on the course website. But anyhow, you're going to get the link of this recording. So the session is recorded. So don't worry about missing any part. You can go back and watch it again. Okay, fine. So let's start with some problems which are actually related to big O. So we'll get that concept clarified first. So let's start with a basic problem. So here is a problem. So I want you to take your time, just read the question properly, and just try to answer it yourself. So basically the whole problem is about an image processing algorithm that is doing 3 steps in it, and each step you are given the complexity of it, and you are asked what is the complexity of the whole application. So just take your time, read the question and try to solve it, and if you get it, you can put your answers in the chat. Okay, so most of the people have answered the thing as B, and we have some A here, and yeah, O and Q is the most time consuming step. Maybe it is O and Q. Yeah, we'll see about that. So before I give you the solution of this problem, let's look at what big O notation is. Alright. So this is the definition from Wikipedia. This is the link here. You are going to get these slides also. I'm going to share them with you. So you can go on these links of Wikipedia, and there is another link of Free Code Camp. So they explain the basic concepts of big O notation, and they'll give you some more examples. So what is the basic definition for big O notation? You will say that fx is equal to O of gx. So you have two functions here, fx, which you are denoting with the big O notation as O of gx. So this will only be true if the function gx is always greater than fx for very large values of x. So this x greater than or equal to x naught is for sufficiently large values of x. This inequality always holds. So what does that mean if this inequality holds? So let's say if you have a function here fx which is let's say log n plus 7, if it's fn in terms of n, it's log n plus 7, then what can gn possibly be? So gn, the basic concept of big O notation is you have to come up with a function which basically captures the highest rate of increase from this log n plus 7. So the logarithmic function has its own rate of increase. But if you come up with functions which have certainly like more like just the increment, or like let's say for example n square or n cube here, so these functions are going to always be higher than log n. for some value of n. So if you are going to plot these functions, like for example log n, and if you plot n cube with like on the same plot, or n square, then what you notice is that these functions are basically going to exceed log n for some value of n, for some high value of n, and then basically log n will always be below that, and then n cube and n square, any other polynomials will be above it. So this is the basic concept of big O notation. So before we basically go into some examples, you can ask if you have any other questions regarding it. Like if you have any questions regarding this concept, that you have to basically see a function, an increasing function, and you have to approximate it with the highest increasing function in that equation. Okay. So if you have any questions, just take your time, look at these equations and see if they make sense to you. Like we should clarify it right here, because a big O notation will be throughout the course you will have to deal with it. So if you're not comfortable with it right now, let's go into it, and we can basically break it down further if needed. Okay. So you can always reach out to me later also on WhatsApp, etc. if you have doubts. But for now, let's look at some examples. So like if you have fn equal to log n plus 7 here, then what would be gn? Like you can put your, like how would you denote it in a big O notation? So you can write your answers in the chat, like O, and then I want the function gn from you basically. You can, like for the first one, f equal to log n plus 7, you can write, okay, so n plus log n. Okay, this n cube again, are you sure? Why do you think it will be n cube? Like we only have log n plus 7 here. Like we are not talking about the last question. Like I am talking about the question that we have on the screen right now. So Patalam, you also have given 2 raised to power n, and we are getting another from Yash, 2n. Okay. So the answer would be O of log n, and this is will be called as the logarithmic algorithm. It solves itself in logarithmic time with respect to n. And if like some people have given answers as root n or 2 raised to power n. So if you have any other doubt or you do not know how log n is coming, then you can ask me here. The basic concept is, like if you say n square or n cube or root n. So n square or n cube, basically n raised to power anything is going to be exceeding much faster than log n. Alright, so if you need to approximate it with the big O notation, then you want a function which is increasing basically as higher as this. Now this log n can be said as O n square, like there is nothing wrong with it, because n square and n cube are going to be increasing faster than logarithm. But it is not the correct, like it's not the closest approximation you can say. Like the closest approximation would be O log n. Like even though n square and n cube would be increasing, and it is technically correct to say that it is O n square and O n cube, but it wouldn't be the closest approximation. And if you will see here in the question before, so we have what is the most accurate and concise description of the complexity of the overall algorithm. So these from the concise or most accurate, these are important. Otherwise, you are going to have confusion between O n cube and O n square plus n cube. So if like B and C option, how are you going to rule one option out? Alright, so similarly, now if you have n cube plus log n, then what are you going to say the value of G would be? You can again put your answers in the chat. For NQ plus log n. Okay, so we have got most of the answers as NQ, which is the correct answer. For those of you who are saying it can be NQ plus N, maybe, even though that could be again technically correct, but it's not the most accurate approximation. The most accurate we have only see NQ, because you can drop the log n term, because log n will not increase as fast as NQ, and essentially what will remain here is just O of NQ. So if you plug in NQ here and your function is NQ plus log n, then you can find the value of m such that for sufficiently large value of x's, this inequality will always hold. So essentially the most accurate representation of this would be NQ, because NQ is the most like highest increasing term in the whole equation here. It's just increasing much faster than the logarithm term. Now we have and so basically any algorithm which is running in O and Q, you say it to be polynomial. So it's a polynomial running runtime algorithm. Now for the last example, it's n square plus 2 raised to power n. What would be the Gn in this case? You can again put your answers in the chat. Okay. Alright. So this would indeed be O2n, and these algorithms are called exponential algorithms because they take much more time than polynomial time algorithms, and a lot of the effort in computer science is towards, if there are some algorithms which are taking exponential time, then to find algorithms for them such that they can be done in polynomial time, and even better would be a logarithmic time. And like these logarithmic, polynomial, exponential have a lot of difference in terms of time between them. So let's say if you have a fixed n input size of 1000, let's say random and arbitrary 1000, so a logarithmic algorithm can finish it in a few seconds, and polynomial will take days and exponential can take years. So it's very essential to come up with efficient algorithms such that they, it's better to come up with a polynomial algorithm if you have an exponential solution. It's even better to come up with a logarithmic solution if you have a polynomial solution at hand. Okay, so coming back to the question that we have here, so what do you guys think? What would be the answer now? And you should actually differentiate between B and C. Like why would it be like B or C? Why not the other? So the people who are writing B, I want you to think about why would it be C.
Directly therefore we take the NQ. Yeah, Ajit, yeah, that is correct. So basically, if you have n cube plus n square, then we draw the lesser increasing term. So if you plot n cube and n square, and actually, by the way, I don't know if you guys know this, but all these things you can plot and check for yourself. It's actually more fun to plot them yourself. So and try to. Okay, let me see if I can pull something up. Alright, so if you go on Google and if you just put things like x squared and log x, so it will plot these functions for you, and it will basically help you to visualize these things better. So if you see here, basically you can just see if you have, let's say, x squared and log x, then what you see is that x squared increases much faster than log x. And so for example here, like this is a log x function in red that you see, and this is the x square function. So here you can see that x square is increasing much faster than log x. So if you are given a question such that O of n square plus log n, so you are just going to say it's O of n square, because log n doesn't increase as fast as any polynomial for that matter. We are going to see more examples later. Okay. Let's move on. So I hope this first problem was clear to everyone. If you guys seriously have any question, any kind of doubts about Bigger notation at this point, just ask me. This is the time when you should get it clarified. You won't get any other chance for this. Yeah. So
when we try to express our in terms of, can I ask?
Yeah. So go ahead.
Hello.
Yeah, Ajit, go ahead.
Okay. When we try to express our functions in terms of the big notation or the smaller notation, smaller notations or the omega notation,
Yeah.
then we needed to always find the function or the expression that is highest increasing as compared to the other expressions that exist into the
Yeah, for the Bigger notation you need to do that. Omega notations have other things, equality you have to take care of, but for Bigger notation basically you just need to see that what are the functions which are increasing as fast as your highest increasing function in that equation. So for example, if you have n square plus n cube, what is the highest increasing function in this? It's n cube. N cube increases faster than n square. And so basically you check out all the other terms which are not increasing fast enough and take your fastest increasing term and you just express in terms of that. Now if there would be two n cube steps here, like let's say that we are doing this convolution step twice, alright, then what would be the complexity of the algorithm? Ajit, do you want to take a shot?
If we do the convolution steps twice, then it will become n to the power 4 order, because we just multiplied, so the number of steps will added up, because n square multiplied then to the power 4. The convolution is nothing but just taking one function into the another function.
Yeah, but we are not doing, so we are just repeating the convolution twice. We are not repeating the convolution n number of times. Then what do you think would be? Yeah, it will be the same.
It will be the odd of
n cube, yeah. So basically if you are just multiplying a constant, or if you are just repeating the same n cube algorithm 3 times, 4 times, 100 times, it doesn't matter. If it's just a constant, then you are going to just get that constant in term of your m here. So what you see as m, so this m will take care of all the constants. You can put in any positive value of n here. So even if it's 3 n cube, 4 n cube, you just write it as O n cube and then be done with it. Okay, let's move on. We have a lot of problems to cover actually. Let's try to pace up now. Alright, read this second question and give me the solution quickly. So in this problem, you need to actually compute. You need to like to rule out one option or other. You have to use these values 400, 4000, and you need to see how by increasing the size of your input n, how much time is getting increased. So in accordance to that, you have to figure out which of the complexities can it be. So you'll need to use a paper and pen basically to actually solve. Like it's a numerical question. We can give just one more minute for people to guess, then we'll look at the solution. Okay, let's look at the. So basically, you are given here 4 inputs which are increasing with as a factor of 10, as one of you guys pointed out. So it's 400, 4000, 40,000, and 400,000. Now, if you basically fit the given time according to what are the things given, so basically 400 square and 4000 square, and if your CPU is doing 10 raised to power 9 operation, it would indeed take 10 raised to power 9. So basically this is assuming, like, so basically here you have to plug these values into each of these possible equations. So if you have n log n, what are you going to do? 400 log 400, 4000 log 4000, and like that you would see that the differences are they actually of the same complexity. But the answer, many of you guessed as n log n, but the answer is actually n squared. So if you're going to plug in these values 400, 4000, 40,000 and 400,000, and you take any fixed CPU step, like this 10 raised to power 9 is not even required. You can have any number of operations and you'll get the same O of n square. Basically how the time is increasing from seconds to minutes is of the order of n square. So just for these kind of questions, what you need to do is plug in your input sizes and see if these were the input sizes, how the time would actually increase. And then you can know if the complexity is n square or n cube or n log n. Like you'll just need to plug in your values of n and see how much time is increasing as n is increasing. Alright, so just remember these kind of particular question where you need to plug in the value and check for complexity. These can be little bit tricky questions. You can really ask me anything about it if you have any queries of how to, maybe you can see these problems again in quizzes or something. So just be careful about these kind of problems and ask me if you have any questions regarding this. Otherwise we move on. And you can switch on your mics and just ask me, like don't worry about anything, don't hesitate.
Okay.
Yeah.
Can I?
Yeah. Go ahead.
We needed to compare the input size in how the input size increases as the time increases the organism.
Yeah. Yeah, that is correct.
यहाँ पर दिया 10 to the power 9 और वो हमने इनपुट साइज इंक्रीज को चेक करना है कि इसके कंपैरिजन में किस इक्वेशन के थ्रू इंक्रीज होगा.
Yeah, that is correct. So if you will let's say put n log n and you plug in the same value like 400 log 400, then if you do 40,000 log 40,000, so the increase will not be from seconds to minutes. Basically here like or basically 40,000 to 400,000 if you go, then 40,000 here was in seconds and 400,000 was in minutes, but with n log n you will get again 400,000 will come in seconds because n log n is much efficient than n square. So only possibility would be n square, and if you go to n cube then it wouldn't be in minutes, it will be in hours. You get it? So basically the hint that you're given is like from 40,000 to 400,000 you go from seconds to minutes, and if it's n log n you are going to actually go from second to second, and if it is n cube you're going to go from maybe minutes to hour. So that is what you need to use, like the time and the input size that you're given. And you actually like just to convince yourself you should really do that, like compute all these values n log n, n square, n cube log n, compute all of them for all of these various inputs and see if you assume that 10 raised to 9 operation per second, how much time you are actually getting, and then you will see that the only answer can be O(n) square. And just practice this problem once and you wouldn't have to do it ever again for these kind of problems. Like they all have the same kind of formulation.
Turn on the camera.
Okay. There was alright. Fine.
Sir, how did you come to this number of 1.6 seconds, 1 seconds?
Yeah. So if your computer is doing 10 raised to the power 9 operation in 1 second, and you needed to do 16 into 10 raised to the power 8 operations, so that will be 1.6 into 10 raised to the power 9 second, right? So that will be like 1.6 second here, because in 1 second you are doing 10 raised to the power 9 operation, and to do 1.6 into 10 raised to the power 9 operation you'll need 1.6 seconds. Yeah. So you are given this, like assuming your typical desktop PC performs 10 raised to the power 9 basic operations per second. Any other questions, queries you have? Yeah. Any other questions you might have? Okay, we'll move on. We are running out of time. Okay, problem 3. This is quite an easy problem. Just go through it. Drop your answers in the chat. mostly PC something. Okay. Think about it carefully. Like, what have we learned so far about big O notation? What does it mean when they say, let's say, Hn is O of Fn? Like, what does this mean? Hn is O of Fn. So that would mean that Hn is increasing at least as fast as Fn. And look in basically Fn and Gn. Fn is just a cubic algorithm and Gn is your like quadruple algorithm. And you are asked about some Hn that is given here. Okay, so many of you guessed right. It is, the answer is B. So basically, so Fn will be O of Gn because Gn has a fourth power here. Alright, so Fn will always basically Gn will be run, it's basically a higher increasing function than Fn. So you can write Fn is O of Gn and Hn is O of Fn, which is given here. So it also must be O of Gn because Gn is actually increasing already faster than Fn. So you cannot have an Hn which is basically O of Fn. So if it is O of Fn, then it must be O of Gn. Right, because Gn is a higher function. So let's say if you have Hn as n squared here, alright, then you can write, okay, Hn is n squared, then n squared is O of Fn, which would be essentially O of n cube. But now n squared should be O of n4 also, right, because it's n squared and this is O of n4. So because O of Gn is definitely higher than O of Fn. So if Hn is O of Fn, then it must be O of Gn also. So if you guys have any doubt, you can ask me. People who guessed it wrong, like, you should really ask me. Like, I know I can already see who guessed it wrong, and I really hope that you guys got it. Like, don't just like, it's not that because few people got it, it's easy. It's not like that. You are here to clear your own doubts. So if you are not getting it, like, just switch on your mic and just ask it away.
Yeah, hello sir.
Yeah, Mohit, go ahead.
If h of n is less than known function, then it might be d is also answer, right?
Okay.
Means I'm thinking that if both is the hn is less than both functions, then what would be the case?
Okay. So see, read the question. Like, always give time to read the question and like, just what it is asking. So what it is asking is which of the following is not possible. Now if you look at the D option, so it is saying Hn is not O of Fn. Alright, so that means Hn is you got it now? Okay. Now these questions actually can be tricky, okay, like you have to, like, because they are trying to make you get it wrong, okay, so you have to be very patient while reading the question, and otherwise it's easy to lose marks in these. Okay. Any other question? Yeah, go ahead.
My doubt has now cleared because I didn't read the not possible.
Yeah, it is tricky. Even when I was reading it first, I was like, what is this question exactly? Like, this happens a lot. Like, you have to read these questions very carefully. And I'm really appreciative of people who are actually interacting and talking these things, because it is very important. Like, it is, you're here for your own learning, right? So let's put an effort into that. Okay, moving on. So, okay, this is a simple question. We're going to just place. So, yeah. Go ahead. Okay, so when you say Hn is O of Fn, so what you mean is basically, see, O of Fn would be nothing but O of n cube. Alright, just drop all the other lower terms and drop the constant. Now if you say Hn is O of n cube, then you say that the function Hn must be either a cubic polynomial, like it can either be n cube or it can be like n square or it can be n, or some n raised to power something which is less than 3 basically, or it could be logarithmic. Alright, so that is what it's meant with Hn is O of Fn. So Hn is at least increasing, is at least as great as n cube, but it can be smaller also. Alright, O of Fn is just basically a higher increasing function, like you are putting like a bound on it, an upper bound. So that is what it's meant by Hn is O of Fn. Is that clear? Like, or should I give you some examples? Okay. Yeah, who's okay. Devji, I'll just come back to you. Let me just clear Yash's doubt and then I'll get back to you. Okay. So Yash, you see here basically if you have like x square and log x, alright. So you see the function x square here, how it is increasing, and you see log x, alright. So basically now what I can say is log x is O of x square. You get it? Like that will be the term that we will be writing. So basically what we are looking for in the big O notation, what goes inside the big O is at least the same degree function as the outside. So what we have here, like in the previous definition, like if you have O of gx, so basically gx should be at least as greater than fx, or fx can be smaller also. So if you have gx as x square here, so fx can be log x. If you have gx as x cube, then fx can be x square. You get it? So if you are saying that Hn is O of Fn, so with that you mean given Fn, so Hn is either a cubic polynomial, or it is a quadratic, or a lower polynomial, or it's logarithmic. So that is the meaning of it. Like I hope you get it now. Otherwise you can always ping me on WhatsApp and we can again clarify these things. Okay, cool. Any other doubts? Devji, you were asking?
Yes, sir. I was just seeing the option A. That how can it be that h of n is after the f of n as well as g of n at the same time?
Okay, so tell me if h of n is n cube, then will the first statement be right or wrong?
Then it will have the connotation of f of n.
So,
And g of n also, it will have and it will have the connotation of g of n.
yeah, so if Hn is n cube, then can you say that n cube is O of g of n, as g of n is given here?
Yes, because g of n is like n to the power 4 term.
Yeah. So for that Hn,
But
so
not
yeah.
but then not because of why would it be also go of
Okay.
but g of n is already there.
See, if Hn is n cube, then you can say that n cube is O of f of n, which is basically n cube. You drop the last terms and it becomes n cube. Alright, so Hn is O of Fn is correct if Hn is n cube. Now, if you say Hn is n cube, then will it also be O of Gn, which will be true because O of Gn is nothing but O of n fourth. And we are going to say that n cube is O of n fourth. N cube is also O of n cube. You get it? Like what comes inside the big O notation is just a function which is increasing faster than what you have outside. So in previously what we had fx and gx, so we just need a gx which is basically increasing faster than this fx. So here if Hn is n cube, then you can say that Hn is both O of Fn and O of Gn. You get it?
I think that f of n is also having the notation of g of n.
Yeah.
Both of them are good.
Both of them are correct, like because Gn is basically more increasing than cubic, like it's on the fourth power. Yeah. Alright. Okay. Okay, so we'll move on to the next problem. This is a simple problem. We'll just quickly go through it. Just write down your answers here.
Charul sir, please share the screen of questions.
Okay. Supriya? Supriya? Fine. One minute, sorry, I have to charge my laptop. Alright, so can you see the problem now? Just put in your answers in the chat. Okay, I think now we are getting the concept right. Yeah. A is the correct answer of these things. As I showed you before, if you look at log x and square root x, then you will have square root x as this rate function which is increasing much faster than your log x. So root n is not O of log n, that's why Tn is not O of n log n. Very well. So I think we are getting the hang of the recommendation with this. Okay, we'll go on the next problem. Okay, this we have basically 6 set of functions, 6 pairs of function, and you need to just see which one will grow higher or lower. So if you'll go at A, then you have n square plus n and 2000 n square. So this I think you all know by now, these are increasing at the same rate. So they have the same big notation. Going on 100 n square and 0.01 n cube, which one will be greater? 100 n square or 0.01 n cube? Okay, yeah, n cube is the answer. Then log n and ln n, which one will be increasing faster? Okay, just be careful. Yeah. It is the same, because with log 2n and ln n the only difference will be that of a constant. Otherwise these both are basically similarly increasing function. Like you can basically write ln n as log of n upon ln of 2, so which will be log 2 to the base e. So basically the only difference between these two functions are a constant. Now log squared n and log 2n squared, what about this one? Which one will be faster increasing, let's say? Which one will increase faster than the other? Log square or log of n square? Which one will take more time? Let's say, like if you have an algorithm which is running log n square, or if you have an algorithm which is running log n, or log square of n, log n into log n. Okay, so we have some divided opinion on it. Okay, so if you have log 2 of n square, this is nothing but 2 of log n. You can get this power of 2 here outside, so you will get 2 log n. And this is nothing but log n into log n. So just think about it. If you have an algorithm which is running log n times, now you are running another algorithm which is log n into log n, versus this algorithm which is log n plus log n. So which will be faster running, log n into log n or log n plus log n? Now you can answer it. So is it log n into log n which will run faster, or log n plus log n? And so this is for sufficiently large n. You can even plug in a big value of n and just solve it, like which will give you a bigger number or a smaller number. Yeah. So 2 log n will be basically a faster algorithm. So like if you have an input of, let's say, n equal to 1000, so and you have a base 10, let's say, so log n would come about 3, so 10 raised to power 3. So for an n equal to 1000, you're going to get either 3 plus 3, which is 6, or 3 into 3, 9. So these are quite close, but as the value of n goes higher and higher, the differences will be much more starker. Okay. Moving on. So now we have 2 raised to power n minus 1 into n. Quickly tell me which one is faster. Yeah, they are the same. Good. What about n minus 1 factorial and n factorial? Which one is faster? And now you guys are just saying same for everything. It's not same. Think about it. This relation.
Hello, sir.
Yeah. Yes, Amit.
Sir, I have one doubt, sir.
Yeah.
In factorial, how can we optimize? It will give bigger values. It will take more time.
So what is your exact question? Like if there are bigger values, they are going to take more time. Yeah, with increasing n. So are you first asking about any of these particular parts, like A, B, C, D, F?
Only if, sir. Factorial. Of
For the factorial. Yeah. Okay. Yeah. So what is your doubt?
We will take bigger values of n. It will take more time, sir.
That is true. Like both of them will take more time. So if as n is increasing, let's say 1000 or even 100,000, so you're going to get very big values here. And for both of the cases, like not just this or this, but for both of them, as n is increasing, your runtime is increasing basically. Yeah.
Yes, sir. How
Yeah.
can we optimize, sir?
Oh, so optimization is actually so these are just theoretical values. If you are actually go towards an algorithm which is running in factorial time, which is just exponential actually. So if they are running in exponential time, then the optimization depends on the particular use case and algorithm that you have. What we are doing here is, if you have these two algorithms, then we are just looking at which one will be faster or slower, or are they actually same. So optimization, we are going to look further down in the course. We are going to actually look at specific algorithms, and we are going to think about ways to do it faster, ways to optimize them. So then you can again think about how to solve a exponential problem into a polynomial time. So that optimization steps you are going to see in the future. Yeah. But for now, I just want you to understand how these big O notations work and how can you basically classify algorithms as slower or faster than each other. Okay. Yeah.
Yes,
I had a
sir.
doubt. I have a doubt.
Okay, Kevin, go ahead.
Yeah. So in option D, what's the answer?
Yeah. So option D, the answer is, so again if you look, log square n is log n into log n, and this is 2 log n, so this will be slower and your 2 log n will be faster. Yeah, so the answer is basically this one will be faster. Yeah.
Why would log square n be slower? I mean, isn't it quantitatively increasing? Whereas, so if let's say I substitute log of n by x, so I have x squared versus 2 of x.
And which one will be slower?
So 2 of them will be slower than x squared.
I think x square will be slower than 2 of x.
Oh, sorry. Okay.
Yeah.
Thank you.
Yeah. Cool. Yeah.
Also, one more thing is
Yeah.
option E.
Uh-huh.
Why is this so? I mean, if I substitute a very large value of 1, let's say 1 million, 2 raised to n will take much longer than 2 raised to n minus 1.
So you're saying it can take double the time, let's say 2 raised to power n by 2 and 2 raised to power n. So it will take double the time of this thing. But what we are talking about here is big O notations. So the big O notations do not care about your constants. They only care about the degree by which the functions are actually increasing. So for them,
n square and 2n square, 3n square, 5n square or 100n square, they are all the same, because they are just, the difference is just of a constant multiplier, right? So if you'll go back to our definition here, like what we had before, the notation here. So if you will have 2n and 2n minus 1, so this m will take care of it, and you will get an equivalency here. So you'll say 2n is big O, or basically 2n by 2 is big O of 2n, right? So you'll get basically the same big O notation for both, because it's just a difference of a constant. Yeah. So that sorry. So basically what we look for in these big O notations is what are the things that are changing with respect to n, right? So if you have like 2n and 2n by 2, then like if you look at both of these functions, then both of them have the same dependency on n. Okay, like the n dependency is same, like they are both exponential in terms of n, but there is just a constant difference between them, and that constant is just 2n by 2, and this 2 doesn't vary as we are varying n, the size of the computation. So basically as we are increasing n, this 2 will not have any role to play, but only this 2 raised to power n will have a role to play in increasing your time, and this 2 raised to power n is common between both of them. So this is also another way to understand it. Basically we only want to focus on the terms which are depending on n, and we do not care about the constants. So even if there would be a plus constant or a multiplier constant, so we do not really care about them because they are not changing as a function of n.
That makes sense. So if it was,
Sir,
I have a doubt.
Okay, Kevin, I hope I cleared your doubt. We can take it up if you are still unclear about anything. Manish, I guess you want to ask something?
Yes.
Yeah.
So suppose we have two algorithms. Algorithm A is having complexity of order of n,
Okay.
and algorithm B is having a complexity of order of nq.
Okay.
So n represents the size of the input, right?
Yeah.
So which one is faster?
Yeah, so if you just see O of n square and n cube, then always n square will be faster than n cube. Like you think about it in terms of, let's say, an array, and it is a size n, so that is your input size n. Now you are traversing this array like either n square number of times, like each element you are like going from each element to each element n times, then n square, or n cube time, then n square will always be faster than n cube. Alright, so with polynomial, basically with polynomials what happens is each degree of polynomial is going to take your algorithm as it will keep getting slow, basically from n to n square, n cube, n4, they will each keep getting slower and slower. Alright, and if you take now exponential 2 raised to power n, so the 2 raised to power n will be slower than any of the powers of n. So if you have n raised to power 100 or even 1000, so even this algorithm will be faster than 2 raised to power n. You get it? So there is a hierarchy in terms of logarithm, then you have polynomials, and then you have exponentials. Okay, so the meeting might end in a minute because Google Meet only allows an hour, so I'm really sorry for this. We have finite time here. Like if it doesn't get ended, we'll continue it. But if it gets ended, I want you guys to join the WhatsApp group that I've floated around on discussion. So I think it will continue. I think it might just continue. But in any case, if you guys have any other query, then I'm going to basically I've already shared the WhatsApp group on the discussion forum, so I want you to just join that WhatsApp group and you can ask more questions there, and there are more TAs that are going to answer them for you. Okay, so this session is almost coming to an end. I'm going to stop with the problem solving here, but you guys can ask me some few quick questions if you have. We are going to run it for maybe more 5 to 10 minutes more this session. Yeah. Yeah, so you'll get the PPT and the recording of this session. Recording will be on YouTube, and PPT will be basically in a Google Drive folder that you'll get the link to. Yeah.
Right. Can you give me the WhatsApp group link? Yeah.
That is on discussion forum. I actually sent it. If you want, let me pull it up. Maybe we can. Let me just see if I can.
Sir, I have shared.
Did you share it? Okay. Cool.
Yeah.
Thanks. Okay, let's go through some questions if you guys have, otherwise we'll wrap up.
I
Actually,
have a question.
yeah, just tell me.
Uh, uh, in the time complexity, we do not care about the size. Means that how much, what is the size of the input. We only care about the number of inputs that means number of operations that being performed by our function.
Okay.
So in a question I had listened from the one student maybe. He talked about the input with the time complexity, so I get confused about it.
Okay. So there are three different things. So one is your input, okay, which is our n here. Alright, like we always talk in terms of these n. So this will be our input, and this can be like a size of your array. So if you have an n element array, or if you have n cross n pixels, so this n will always be like number of elements that you have. Okay, now we talked about two things. So one thing is basically the space that the algorithm is taking. So that is the size complexity of the algorithm, like how much memory do you need to run it. Okay, so most of the questions or discussions that we are going to have will be related to time complexity, because we really do not care about space complexity that much. Like as computers are getting more and more advanced, you are getting free RAM almost, so you have like a lot of RAM available, so memory constraints are mostly not so much unless you have like embedded systems where you have memory constraints. So mostly the algorithms are looked in terms of the time complexity, and which is what we calculate in terms of these O and square, or whatever you see here. Like the big O notation generally is calculated in our cases for time, and in terms of the size of the input, which is n. So there is size of the input and the space that the algorithm takes. So these are two things, so don't get confused between them. So n will be your size of the input, which will be like number of elements in the array, and there's another space thing which we are not going to, we'll seldom talk about it, and it just needs to be taken as size of the input and the time complexity of it. So just focus on these two things. Yeah. Okay, like I hope I cleared it and you're not more confused.
So in this question,
Yeah.
we compared root of n versus
Mhm.
log n.
Yeah.
We said that root of n is not equal to log n, since n square and n square cancel out.
Yeah.
If I go with option B, can't I make it so that it's n square equal? Then can't I compare n to root n?
And what will you get?
And in that scenario, they are also not equal. I mean, root of n is not equal to n.
But is root of n not O of n?
Root of n, O of n. No, it's not, right? Because the exponent is not the same.
N has 0.5, and like root n will have 0.5, and if you just have O of n, it will have 1. And if you plot n and root n, so which one do you think will be more increasing?
N will be slower than root.
Okay, slower in the sense, do you think n would be taking higher values than root of n, or do you think they'll intersect at some point? Yeah, yeah. So yeah, if you just put in, let me see if I can plot square root of x and x for you.
They will intersect. They will intersect, but n will overshoot root of n over n.
Or what will overshoot? Square root? N will overshoot square root x, right? See, okay, so you have here x and square root of x here in blue. So what you are saying is correct, they intersect, and then x basically overshoots square root of x. So what can you say from here? You'll say square root of x is O of x, will that be correct?
Maybe my understanding is wrong.
Okay, okay.
In my opinion, the big O notation will be different. One is big O of n, one is big O of a.
Okay, so like the concept that you're getting confused about is, so n square, like let's say I have a function n square. Now n square you will say is a big O of n square, that is correct?
Yes.
But it is also a big O of n cube or n4 or n5. So basic, yeah. So
for that, what you need to just focus on is just this equation that we have. Just solve it for like plug in a few functions of fx and gx and see what happens in it. So if you have fx as n here, alright, and you have of O of n square, okay, so n square will definitely be greater than n for some value of x, you get it, or for some value of n. And so basically the function n, you can call it O of n square or O of n cube or O of n4 or anything, because these are all higher than n, alright. But when you are asked about the most accurate and concise description like this, then you try to get as close to it as possible. But it is technically correct to say that any algorithm which is O of n square is also O of n cube. Okay, like, but it is not the closest approximation. The closest you'll get is n square in that case, in particular cases. So like big O just sees if the function inside the big O notation is higher than the one outside or not. So in this case, if you had n and root n, then the function inside the O, which is n, will be higher than root n, and which will be correct. So here this is actually correct. Tn is O of n cube, because makes sense? Exactly, it's an upper, it's basically a lower bound in that sense. Yeah.
Makes sense.
Yeah.
Thank you.
Okay. Fine. We can take couple of questions if you have. Okay, Yash, go ahead. Yash, are you saying that you'll need more questions like these?
Yes, sir.
Okay, so what I'm going to do is there are actually a lot more problems in these slides, and I'm going to basically give out these problems to you, but I am not going to give out solutions of these problems, not at least this week, but maybe either in the weekend I'll give it, so that you have enough time. And these are just practice problems, so these are just for fun. So I'm just going to throw these problems out, and I'll give you the solutions by Saturday or Sunday. You can just attempt them by then, and if you have any doubts or you don't understand any solutions, then in the next session on next Tuesday you can come back to me and we can look at some of the problems. Like there might be some tricky problems in there, so basically just be careful. It's okay if you don't get the solution right away. You can always discuss it next week. Okay, so this whole slide I'm going to just give it to you, and you can solve these problems by yourself, and we'll discuss the next week. Okay, cool. I hope it was I think it was a fruitful session. I had fun interacting with you guys, and I hope you have a good positive journey going forward in this course, and I hope that more of you guys will interact, but I'm happy that enough interaction was there in this session. But I just want you guys to open up a little more from next session, because I really want you to clear your doubts here. Like this should, if you're putting in the effort, you should get the results of it. So yeah, in any other cases, whatever queries you might have, hit me up on WhatsApp, and we can discuss them. Yeah. Okay. Any other things from you guys? Nihil, saying something? Okay, fine. In case you don't have any more queries, I'll wrap this session up.
Hello?
Yeah, Nihil.
Yes, I have a doubt. So we have learnt about like upper bound functions, lower bound, and then tightly bound. So anyway, we can relate these functions together.
So basically, you have to see it in this manner that with big O notation, we are basically going for a lower bound. Okay, and so we have to look at it in that time. And in terms of omega notation, we are going to be looking at the equivalency of the function. So they both have different approaches to that, but for specifically bigger notations, you just need to see that the function inside the bigger notation should be basically increasing the function outside after some large values of n. So if you are talking about bounds, so just look at in this way, like which of the function is going to be above the other function. Okay, and omega notation is you're good to know that we are not going to use it, or we don't talk in terms of it. So like bound you should always see as the tightest bound that you can get. So if you have like polynomial n cube plus n square plus something, then you are just going to say O of n cube. Okay, because that is the tightest bound that you can find. It will be in constant multiples, you can get it for some greater values of n. Okay, so just think in terms of about that, like bigger notations, and just go through some problems of bigger notations, and then you'll get the hang of it. Yeah. Okay, and we can discuss further in any specific questions that you might have. I'll be happy to take it. Okay, so we'll wrap this session up. Thank you guys for joining, and I'll see you guys on next Tuesday, same time, 6 to 7, and it's the same link. Yeah. Okay, so, bye bye. Take care.
Thank you, sir.
Yeah, welcome. Welcome.